Hello 20-1s. Welcome to the continuation of radical calculations. Got to be honest with you, this is the third time I'm doing this video because of technical glitches. So if I sound a little angry, or if I go a little bit too fast, it's because this is the third time I'm doing this. So maybe you have to pause it every now and then. Not real complicated with multiplying radicals and dividing radicals, which is what we're going to do today. But it's important that you understand how the process works. So very quickly, just if we look back to what we talked about yesterday, 2 root 5 plus 7 root 5. I drew the comparison that this is kind of like working with polynomials. 2x and 7x go together because they're like terms. So that just tells us we have a total of 9x's. Here, 2 root 5 plus 7 root 5. Well, this is like saying we have 2 root 5s, we have 7 root 5s, so altogether we have 9 root 5s. So we combine radicals just like terms in a polynomial. Well, it's not going to be a lot different when we're multiplying radicals. If we're multiplying two terms in polynomials, what are we doing here? Well, we're multiplying coefficients, and then we're multiplying the variable components. And how do we multiply variable components? We add exponents. So we need to work with coefficients and variable components separate. Well, that's not going to be any different than multiplying radicals. Because what's the first thing we do? We multiply coefficients. Second thing we do is we multiply the radicands. And then we look to simplify if possible. Now, the reason this multiplying radicands process works, if we think back to where we talked about simplifying, if we had root 24, well, and we wanted to simplify it, we've talked about in order to simplify and make the radicand smaller, we can think of this as root 4 times root 6. We split the radicand into two separate radicands. Well, now we're just doing the exact opposite, is we're taking two radicals with radicands of 4 and 6, and we now want to write it as a single radicand. So whereas we've been going this way for simplifying, when we're multiplying, it's just kind of going back the other way. So here we go, page 8 if you're not there. Page 8, root 3 times root 5. Coefficients of 1. What do? Multiply coefficients, multiply radicands. We get 1 root 15, which is better written. We don't need the coefficient of 1. It's just root 15. Can we simplify that radical 15? Can't break it into products or into factors. They're rootable, so root 15 is our product. Root 3 times root 8, same idea. Technically, there's coefficients of 1. Multiply coefficients, multiply radicands. We get 1 root 24. Again, 1 root 24 is the same as just root 24, but in this case, we have some simplifying that could be done, because 24 we could think of as 4 and 6. The 4 roots out to leave us with a 2 when the 4 gets rooted out, but we still have the radicand of 6. So the product of root 3 times root 8 is 2 root 6. This one's not in the booklet, but really quick. If we had 3 root 5 times 6 root 10, let's calculate this one. Not in the booklet, but quick calculation. What's the simplified product here? Well, multiply coefficients and multiply radicands. So after the multiplying, our new product is 18 root 50. Yes, that is the correct product. It's not in the best form because our 50 could be broken into 25 times 2. The 25 could be rooted out and it would become a 5. So 18 times 5 is 90, and we'd still have the radicand root 2. So 90 root 2 would be our product. Now these questions can become a little bit more complicated. Take a look at questions that involve variable components. Process doesn't change, but the math becomes a little more complicated. 5 times 7, there's our coefficients. And now we multiply radicals. Remember, when we're multiplying variable components, we add exponents on like bases. So 2x times 3x is a 6x squared. 35 root 6x squared is the product, but it's not simplified yet. The 6 can't be simplified, but x squared could be rooted out because the square root of x squared is an x. So we would have to multiply the 35 by an x, and we still have the radicand of 6. There's your product in the simplified form. Give the next one a try, and then we'll talk. Here, 4 times 5 is 20. 6y cubed times 2. There's our radicand. 6 times 2 is 12. Y cubed times nothing is a y cubed. So we got 20 root 12y cubed. There's our product, but it's not simplified. Simplifying here, there's a lot of pieces, so I'm actually going to write it out a little bit better. 12, we could think of as 4 times 3, because the 4 could be rooted out. So our coefficient would have to multiply by 2, because the 4 being rooted out is a 2. But the y cubed also has to be dealt with, and we've practiced it. To square root, we need an exponent that's even. So our y cubed could be broken into y cubed times y1, y squared times y1. Y squared can be rooted out because the square root of y squared is a y, and we still have the y that will be part of the radicand. So when I do all this simplifying, 20 times 2 times y is 40y, root, and we still have a radicand of 3y. And there's the simplified product. Make sure you're simplifying. If we move on to page 9, dividing radicals. Real quick with dividing radicals, because this is not a big stretch. What are we going to do? We're going to divide coefficients, and then we're going to divide radicands. And as always, we will simplify if possible. But again, dividing radicands, why does this work? One of the first root or radical properties we talked about is we said if you have a fraction in a radical and it doesn't look easy to work with, we could work with the numerator and denominator separate if we wanted to simplify. Well, this is exactly what we're doing. We're dividing two radicals, divide the radicands, which means we now have the root of a divided by b, which is just, again, going backwards to what we have been doing. So here we go. 12 divided by 6, divide coefficients. Radicand, 6 divided by 2. And our quotient is 2 root 3. No simplifying to occur. Second example, 24 divided by 6 is 4. 54x divided by 6x. Remember, we're subtracting exponents when we divide powers. So we end up with root 9 and x to the 0, because x1 minus 1 is x0. Does x0 do anything? No, we don't need it. Simplify, well, in this case, 9 is a perfect square. So when we root out 9, we've got to root out the value of 3, which leaves us with 4 times 3. And there's nothing in the radicand because all, or in the root sign, because all of the radicand rooted out. 2 more questions on page 9. Give them a try, and then we'll talk. I'm actually going to look at the second one first. It's a little more straightforward. There's something about the one on the left there that I'll talk about in a minute. But coefficient of 1, if it helps to put that coefficient of 1 so you have something to work with, do it. 3 divided by 1, divide your coefficients. 32 divided by 8 leaves us with a root 4. 32 divided by 8 is 4, but we can square root 4 because that is a perfect square. When I root out a 4, all of it roots out to become a 2. So 3 times 2 is 6. The 4, the radicand has disappeared, and our answer is 6. Now this other one, though, we have to be careful because when we divide the coefficients, we have 5x divided by 10x, and then our root 20x squared isn't being divided by anything, so we just have root 20x squared still. There is nothing there to work with, to divide by. It's just a root 20x squared. But when we divide, x divided by x, those just cancel each other out. We're left with 5 divided by 10. Don't go to decimal form. Just take the division in fraction form. If it doesn't divide even to a whole value, leave it as a fraction. We get 1/2. And that's still with a 20x squared. Can we simplify? We can. 20 can become 4 times 5, so we can root out the 4, which means we're rooting out a 2. So we have to multiply our coefficient by 2, but also we can root out an x squared because the square root of x squared is x. So 1/2 times 2 times x is just a 1x. And we still have the radicand of 5. There's our quotient. So multiplying and dividing radicals, pretty straightforward process. A little bit of division. Now, page 8. Let's go back to page 8. And here's what math loves to do, is to take multiple concepts and incorporate them together. So here's the initial value. We have a square, it says, with an equilateral triangle inside. Has an area of the square is 32. We want the perimeter of the triangle. So the perimeter of the triangle is what we want, but we need to know side length first. Well, our triangle says we have a 32 centimeters squared area, and when you have a square, side length is the square root of the area. Because it's side times side to get 32, we're going to square root the 32 to get a side length. Simplified though, this is 16 times 2, so the side length, root out the 16, is 4 root 2. There's your side length. If we know the side length of the triangle and the square is 4 root 2, that means the perimeter of the triangle will be 3 of the 4 root 2's. So, coefficients, 12 root 2. There's the perimeter of the triangle. Well, now, we know the perimeter and we know some other information about our triangle. This question is saying, what's the height of the triangle? Well, remember on a triangle, when we draw a height, that means the height creates a right angle triangle. So I'm just going to draw this a little bit bigger, but to get the height of the triangle, again, in our diagram at the start, we just want half of that triangle. So if I have half that triangle, it's a right angle. We know that this length of the triangle is 4 root 2 because that's the length of the sides. And we want to get the height of the triangle. Well, we do know that this length is half of the whole thing. So this is like saying we have 4 root 2 divided by 2. How do we divide? Divide coefficients. And root 2 divided by nothing stays as a root 2. So we now have 4 root 2 for a length. We have 2 root 2 for a length. We're trying to find this other side. Well, right triangle, you have 2 sides. What's going to help with the other side? Our good friend Pythagoras. So in this case, because the hypotenuse is given, c squared minus a squared will equal b squared. So we're trying to find the b squared side. Again, Pythagoras is you've worked with a lot in the past. We're just incorporating values we haven't normally worked with. So our c, our hypotenuse, is 4 root 2, but we have to square it. We want to subtract the other side that we know. which we've called 2 root 2. So we have 2 root 2, and we want to square that. And that's going to give us our b squared. Well, we got to do some calculations. First calculation is 4 root 2 squared. So 4 root 2 times 4 root 2, 16, root 4 using the rules of multiplying radicals. 4 can root out, which becomes a 2. So 16 times 2, we get a value here of 32. Now I need to do 2 root 2 squared. So 2 root 2 times 2 root 2. 2 times 2 is 4. Radicans is a root 4. Root out the 4, which gives us a 2. So 4 times 2 is a value of 8. So we have 32 minus 8 equals b squared, which is the same as 24 equals b squared. But as I know you all know, Pythagoras always finished by square rooting, so we can get b by itself. It'll be b root 24 is our b value. Don't go to a decimal form if we can leave it in exact values. And again, finish this off. Always try to simplify, which we can in this case because it's 4 times 6. So 4 will root out, and our b value will be 2 root 6. There you go. So we can find the height of the triangle using Pythagoras and the dimensions that we've calculated. Last one is to find the entire area. Well, if you recall, area of a triangle, base times height divided by 2. We know the base of that triangle is 4 root 2. We now know the height of the triangle is 2 root 6. So to get the area of it, 4 root 2 times 2 root 6 divided by 2 using radical calculations. 4 root 2 times 2 root 6, multiply coefficients, multiply radicans, divide by 2. How do we divide? 8 divided by 2 leaves us with 4 root 12 for an area. However, simplify if possible. 12, 4 times 3, root out the 4, which becomes a 2. And we're left with 8 root 3 as the area of that triangle. So lots going on there, lots of little calculations, multiplying and dividing radicals. Now as we move on, if we go back to page 9 isn't new information, it's just how do we use this new multiplying dividing process. Well, instead of just always having a radical times another radical, well, we could have a single radical times a multi-termed radical, or multi-termed expression, which has radicals in it. It's not new. It's just incorporating previous processes with new information on calculations. We have to distribute. That's not new to us. It's just the calculations are new. So we would have 2 root 3 has to multiply by 5, and 2 root 3 has to multiply by 4 root 7. I wouldn't expect to see these steps. Just showing it to you, you should be able to do this quickly and efficiently. But if it helps to show steps, coefficients is 10, root 3 times nothing is a root 3. 4 times 2 is 8, 3 times 7 is 21. So we end up with 10 root 3 plus 8 root 21, root 3 root 21. No simplifying there. Neither of those can be made smaller. So we get 10 root 3 plus 8 root 21 because the distributive property can occur with radical values. Here's another one, page 9. Give it a try. See what you come up with. What we need to do, the single radical has to multiply by both terms in that expression, and there's 2 radicals. So what do we have? 3 root 3x times 4 root 2x. 12. Make sure you follow the exponent laws. Root 6x cubed, because we have to add our exponents. 3 root 3x times negative root 7x cubed. If it helps, put a coefficient of 1 out front if you need that. Coefficients is negative 3, and our radicand, when we multiply them, gives us 21x to the 4. There's the distributive, but now we have to look for simplifying. Simplifying this radicand, the 6, nothing I can do to root anything out, but my x cubed could be an x squared times x. So the x squared will root out to become an x. So we're left with 12x root, and we still have the 6x in there. Subtract 21x to the 4. 21, can't split that into any factors that are rootable, so we're going to leave that. But x4 can be rooted out because even exponent means x squared is the square root of x to the 4. So we're left with negative 3x squared root 21. Root 6x, root 21, not like radicals, can't combine those two. So there's what we have. Just incorporating previous processes with the new calculation knowledge. Polys times polys. Well, 2 terms times 2 terms. FOIL. Make sure you perform FOIL here using radical calculations. We end up with 3 root 4 plus root 12. Negative 18, oops, sorry, my bad. Negative 3 root 12, coefficient of 1 out front. And then the last calculation, negative root 36. There's what you're looking at for the FOIL steps. Now we can simplify. Well, to start with, root 4, perfect square, comes to 2, we're left with a 6. 12, 4 times 3, root out the 4, we're left with 2 root 3. 12, 4 times 3, root out the 4, multiply that coefficient by the 2 that's been rooted out, negative 6 root 3. And then 36 is a perfect square itself, root it out, we're left with negative 6. Like terms, 6 and a negative 6 cancel out. 2 root 3 and negative 6 root 3 are like radicals, negative 4 root 3. There's the product for that initial calculation. Simplifies down nicely. This next example you can give a quick try to, but please remember, ladies and gentlemen, this is what drives us nuts as teachers. Exponent 2 doesn't just mean square that and square that. This has been discussed. When you have a binomial being squared, you need to multiply the binomial by itself, which means it's a binomial times a binomial, and you must perform FOIL. Make sure of that. When you perform the FOIL steps, 9 plus 15 root 2 plus 15 root 2 plus 25 root 4. There's your steps for the FOIL. Can we simplify? Well, root 4 can be rooted out. It's a perfect square, so that needs to be times 2 because all of the 4 gets rooted out. 25 times 2, that whole thing just becomes a 50. So we're left with 9 plus 50, and then 2 like radicals because they have the same radicand, and that becomes 30 root 2's. There's your simplified form. So again, previous processes don't change. Calculations you have to be familiar with because we're continually introducing new types of numbers. Last little bit here on page 10 is special products. This has to do with multiplying because that's what a product is, the answer for multiplying. But this is important little bit of information. 2 situations. Here's your first one. Root A times root A. When you have a radical times a radical with the same radicand, your answer is just the radicand. If you can learn to recognize that, these calculations become really quick and easy. Root 3 times root 3, multiply your radicands. 3 times 3 is 9, but 9 is a perfect square. We can root it out. Root of 9 is just 3. Your product is the radicand. Learn to recognize it because it will save on time. It's become efficient. 5 root 6 times 2 root 6. Here's all the steps that you could show. Multiply coefficients. Multiply radicands. Now we can root out the 36. Root of 36. All of the radicand roots out to just become a 6. We get a value of 60. Now, as you move on, a little bit more efficient way to do this, multiply your coefficients. You get 10. But now you see root 6 times root 6. Oh, wait a sec. Radical times a radical with the same radicand. That's just 6. So 10 has to multiply by the 6, which is 60. Anytime a radical with the same radicand multiplies by itself, your product is just the radicand. Now, one step further now with that is this situation, which will become quite important as you do the next lesson. These are called conjugates. Now, conjugates mean you have the same radicals in two separate two-termed expressions. Root A and a root B, root A and a root B, but we have different signs, positive and negative. When you have those situations, we can see that our answer simply becomes the radicand and the radicand with a subtraction sign. It just becomes radicand A minus radicand B. Root A times root A is just A. Root B times root B is just the B. That's a conjugate. Here, I'll show you, because this really is a FOIL situation, here's why it works. Root 6 and a root 2, root 6 and a root 2, addition sign, negative sign. Here's a conjugate. If you do FOIL, root 6 times root 6, well, we just talked about that. What does that mean? That means 6. Root 6 times negative root 2 is a negative root 12. Finish off the FOIL, root 2 times root 6 is a positive root 12. Root 2 times negative root 2. Well, root 2 times root 2 is just 2. There's that little trick we just talked about, but a positive times a negative is a negative 2. But because we have different signs, we end up with a negative root 12 and a positive root 12. These two terms for conjugates will always cancel out. Your OI, outer, inner, the OI of FOIL, when you have conjugates, will always cancel out, and we're left with 6 minus 2. Our 6 subtract our 2, just like the rule says. And we finish with 4. Those OIs will always cancel out and just leave you with your A subtract B. Nice, easy, and this is going to be important in the next lesson. One more time, root 13 plus 2 times root 13 minus 2. Conjugates, root 13 and a 2, root 13 and a 2, but we have the different signs. That makes a conjugate. If you recognize a conjugate, well, what does that mean? It means we do root A times root A, which is just our A value, 13. We also have to do the second term and the second term. Well, in this case, 2 times 2 is 4. We're not square rooting, so that would just stay as a 4. And it's a negative because it would be a positive and a negative. 13 minus 4 is 9. If you recognize this as a conjugate, 13 minus 4 is 9. Nice, quick, and easy. If you don't recognize it as a conjugate or you want proof that that's a quick, easy way to do it, here we go again. Root 13 is a 13. Negative 2 root 13. Positive 2 root 13. Look at that. Outer, inner, the two middle calculations. Negative and positive of the same thing. The o's will cancel out, and we're left with subtract 4. 13 minus 4, there's your 9. There's your rule for conjugates, which we will build on next day. There's your assignment. The math itself, calculations aren't too complicated, but making sure you know what calculations to do at what time and simplifying. It's recognizing the simplifying. Those of you who want to stay on top of this stuff, in the booklet, pages 20, 21, 22, answers are there. Those are some review sheets. It covers everything from the unit, so there's some stuff there that might not make sense to you yet, and it shouldn't because we haven't finished the information. However, there's lots of information on that extra practice that if you want the extra practice, you want to review what we've already covered to stay on top of it, it's all there. Hope that makes sense. Hopefully that my technology will work this time. Have a great day, everybody.